Welcome to the Depth Dive. Today we're jumping straight into some source material on high-quality 3D scene generation. We're looking at a method called FlashWorld, and the claim is pretty bold. Generating full, complex 3D scenes from just one image or even text in seconds.
Yeah, seconds. And that speed really is the headline. You have to remember, traditionally getting good 3D scenes, especially complex ones, it's been computationally very heavy. We're talking minutes, sometimes, honestly, hours of waiting for a render.
Hours, right.
So FlashWorld, according to the research, claims not just speed, but also superior quality. They're saying 10 to 100 times faster than previous methods.
Let's put some numbers on that speed because the figures in the research are quite something. You look at older methods, say CAT3D, that took 77 minutes on an A100 GPU.
77 minutes, yeah. That's a long coffee break.
Or even something more recent like Wonderland. Still 5 minutes on that same high-end hardware. FlashWorld is claiming 9 seconds? 9. On an H20, which is, well, not quite an A100.
Right. Going from over an hour to under 10 seconds. It's not just faster, it's just a whole different way of doing things.
So what's the fundamental change? How did they make that leap?
Okay, so the dominant way for a while was what they called the multi-view-oriented approach, MV-oriented. It's basically a two-step process. First, generate a bunch of 2D pictures from different viewpoints. Then, after you have those views, try to reconstruct a 3D scene from them.
Ah, okay. But I guess if you make the pictures separately first, they might not perfectly match up in 3D space.
That's the problem. There weren't strong 3D rules applied when making those initial 2D views. So the final 3D model often had, geometric issues, things slightly out of place, or textures looking noisy or blurry. It wasn't really coherent.
So the MV way had quality issues stemming from that lack of 3D consistency. FlashWorld must have gone a different route.
They did. They leaned into a 3D-oriented approach. This means the model works directly with 3D representations from the get-go. Specifically, 3D Gaussian representations, or 3D-GS.
3D-GS. Remind us quickly what that is. It's not traditional polygons, right?
No, not polygons. Think of it more like a cloud. Millions of tiny, colored, semi-transparent spheres or Gaussians. The key is, this representation is inherently 3D consistent. And you can render views from it very, very quickly.
But wasn't there a catch with the 3D-oriented methods, too? Didn't they sometimes look less sharp?
That was the trade-off, historically.
Yeah.
Better consistency, yes, but often the visual quality wasn't quite there. Blurry results, maybe lacking fine detail compared to what the best 2D image models could do.
Okay, so FlashWorld needed the visual punch of the MV approach, but the consistency and speed potential of the 3D approach.
That was the goal, bridging that gap.
Right, the 9-second goal.
Yeah.
So how did they actually combine those strengths? You mentioned a dual-mode training idea.
Yes, it's built around a two-phase training strategy. Phase one is what they call dual-mode pre-training. They start with a multi-view diffusion model, but here's a key detail. They initialize it using a video diffusion model prior.
Interesting. Why video, not just a standard image model?
The sources suggest it helps with coherence across views and scales better. Using a video prior apparently helps the model learn relationships between multiple views more naturally and handle higher resolutions, getting it ready faster. This pre-training sets it up so the model understands both ways of generating the high-quality MV mode and the faster 3D mode right from the start.
Okay, foundation laid in phase one, but the 9-second speed, that has to come from phase two, right? The distillation part.
That's phase two, cross-mode post-training distillation. And it's a clever asymmetric setup. They take the MV-oriented mode, remember, it's slow, but produces great-looking images, even if geometrically shaky, and they freeze it. It becomes the teacher. This teacher provides guidance, specifically score distillation gradients, to the student.
And the student is the 3D-oriented mode.
Correct. The 3D-oriented mode is the student. Because it's built on 3D-GS, it already has the geometric consistency built in, so it learns the visual quality distribution from the teacher, the nice details, the lighting, without inheriting the teacher's geometric flaws.
Ah, I see. So the student keeps its good structure but learns to paint better pictures from the teacher.
Sort of like that, yeah. It learns the high-quality look while staying true to its own 3D nature.
And how does that distillation process lead to the speed up, the 9 seconds?
Because the student model gets so much better at predicting the final clean image, it needs far fewer steps in the denoising process during inference. Cutting down those denoising steps is the primary way they slash the generation time down to that sub-10-second mark.
Makes sense. Fewer steps, faster result.
And there's one more piece here during post-training, something called the cross-mode consistency loss, or LCMC.
LCMC, what's its role?
It's basically making sure the two modes don't drift too far apart geometrically. Without it, the sources say the fast 3D mode could sometimes create weird artifacts, things floating where they shouldn't, or duplicated objects. So the LCMC acts like a sanity check, ensuring the final scene geometry remains stable and plausible.
Got it. Distillation for speed and visual quality. A CMC for geometric stability. But, real-world scenes are messy. Lots of different styles, objects. The sources mention that the high-quality multi-view datasets used for training can be quite limited in variety. How does FlashWorld handle inputs it hasn't quite seen before?
That's a really important point for practical use. If a model only sees perfect curated data, it often struggles with novel inputs. So FlashWorld uses what they call out-of-distribution data co-training during that same post-training phase.
Out of distribution, meaning stuff outside the nice, clean training sets. How do they get that data, especially multi-view data, which is hard to come by?
They get creative. They take huge amounts of readily available single-view images and text prompts, like general web images, video frames, things from data sets like Echo 4.0. And then crucially, they pair this diverse visual data with randomly simulated camera trajectories.
Simulated camera paths, where do they get those from?
They simulate paths based on patterns seen in large real-world datasets known for camera movement, like Real Estate 10K and WorldScore. These provide realistic motion pans, tilts, complex paths. So they're essentially creating synthetic multi-view training examples by combining diverse single images with plausible camera movements.
So it's like showing the model tons of random pictures and teaching it, if you are moving the camera like this around this object, here's how the views might look.
Pretty much. It exposes the model to a much wider range of styles, objects, and conditions than it would see in the curated multi-view datasets alone.
And the result is better generalization. It becomes more robust.
That's the idea. It helps the model adapt better when it encounters truly new or out-of-distribution inputs during inference. Makes it more flexible for real-world use cases.
Okay, the architecture sounds solid. Let's talk results. How does it actually stack up when generating from an image, for instance?
Looking at the image to 3D results, specifically figure 4 in the paper, FlashWorld seems to do a good job with detail. It manages to reconstruct fine structures, things like leaves on trees, intricate patterns on fences, even octopus tentacles, according to one example, where some other methods, especially MV-oriented ones, produced results that were maybe noisy or geometrically less accurate.
And for text to 3D, generating purely from a description.
The tables, like Table 1, show FlashWorld performing well quantitatively. It scored highly on metrics like QAlign IQA+ and CLAP score across several benchmarks, T3 Bench, DL3DV, WorldScore. Qualitatively, the paper mentions it generating objects that match the text prompts accurately, getting details like animal fur right while maintaining that crucial semantic consistency.
You mentioned WorldScore. That's a benchmark that looks at both quality and how well the generation follows the prompt, right?
Yes, and on WorldScore, FlashWorld reportedly achieved the highest average score overall, 68.72, and again, the fastest time at 9 seconds. Notably, it also scored highest specifically on style consistency. That ability to maintain a consistent look and feel across the scene likely ties back to using 3DGS and that LCMC loss we talked about.
Ah, the LCMC loss again. Did they test what happens without it?
They did, an ablation study. The version without the LCMC loss actually scored okay on the automatic metrics, the quantitative numbers. But when they looked closely at the generated scenes, the qualitative results showed problems, those unstable floating artifacts and duplications.
So the numbers looked okay, but the actual scenes were a bit wonky without that consistency check.
Right. It really highlights that the LCMC is vital for structural stability and visual plausibility, not just hitting certain benchmark scores.
So summing it up, FlashWorld seems to represent a really effective way to merge the visual quality we expect from top-tier 2D models into the challenging, geometrically constrained world of 3D scene generation. And crucially, they've done it while achieving speeds that make this kind of technology feel much more immediate and usable.
Absolutely. And there's one last point from the sources worth pondering. They explicitly state that FlashWorld doesn't use direct depth information for supervision. No 3D scans, no LiDAR data fed in, yet because it uses that 3D Gaussian splatting representation, it manages to learn meaningful geometry, essentially understanding depth purely from supervising on 2D images.
Just from pictures.
Just from pictures. Think about that, a model figuring out the 3D layout of a scene just by looking at how things appear in 2D views. That ability to infer structure from appearance alone. Well, that's quite powerful, especially when you think about the difficulty of acquiring large-scale, accurate 3D ground truth data.